All right, we're talking about another conic section, hyperbolas. So here's what a hyperbola is geometrically. If you have the two cones, right, it's a conic section, and if you have a plane that intersects them, a vertical plane that intersects them, it's going to trace out two different parts, right? There's an upper part and a lower part. And that's what a hyperbola is, okay, is that orange part of the intersection. So hyperbola has two different parts, right? Here's one part and here's the other. And there's a lot of different things, so it's okay. Let's just think about this here. All right, so here's the major axis. Okay, the major axis is the axis that the two curves open along, right? This opens along the x-axis. So we call this the major axis. We call this the vertex, okay, where the major axis we don't call it the major axis, we call it the transverse axis. Sorry. Major axis is when we're talking about ellipses. For a hyperbola, it's the transverse axis, okay? The vertex is here where the hyperbola intersects with the transverse axis. And here's the center. Okay, notice that the center isn't even like inside the hyperbola, right? So here's the center. Here's and the vertex is this far away, right, from along the transverse axis from the center. And here we have two focus points like we did with ellipses, but these are different. These are inside these two curves, right? So there's a focus point here and a focus point here. So they are like on the other side of the vertex. So for ellipses, the focus was between the vertex and the center. For hyperbola, the focus is on the other side. The vertex is in between the focus and the center, okay? All right, we still have these points called covertices or covertex. Here's a covertex, here's a covertex. But now we have this like green dotted box, okay? We'll talk more about that, but that's what we're gonna do. We have our covertex and our vertex. And then once we have those, we're gonna draw a little, if we need to graph a hyperbola, we're gonna draw this little green box and then draw these orange lines between the two corners, okay? Those are those tell us how we're gonna draw our hyperbolas. So notice those are like asymptotes for these hyperbolas. Okay, they intersect at the vertex, they start at the vertex, and then they go up along these asymptotes. Okay. And I forgot to mention this axis is called the conjugate axis. So we have our transverse axis and our conjugate axis. So yeah, there's a lot of terms. There's a lot of stuff in these diagrams. It's not that bad. Okay, it looks kind of complicated at first. You'll get the hang of it. These aren't that bad. All right, so like what does this mean, right? With the ellipse, we had the two focus points and the string, and we could draw a picture. Hyperbolas, it's not that intuitive, okay? For hyperbolas, what it means is that the difference, so for an ellipse, the sum of D1 and D2 was the same for all the points. For hyperbola, D1 minus D2 is the same for all the points on the hyperbola. I don't have a lot of geometric intuition about that. If that gives you something to think about, awesome. The difference between D1 and D2 is the same for all points on the hyperbola, where let's see, D1 is going to be the distance from the focus point to a point on the hyperbola. And here's the other focus point, right? So the difference between D1 and D2 is constant for all the points on the hyperbola. It is what it is. All right, so here's two things we're going to use. So just like with the ellipse, I'm going to show you how you can derive the equation. You do not need to derive the equation or even pay attention to it if it stresses you out. If it seems like it might be interesting, you should look at it. All right, so here's two observations we need to think about. A, we're going to call the distance from the center to the vertex. Okay, so here's A, here's negative A. So A plus C minus C minus A equals 2a, this distance here. You can think about that, convince yourself that's true. And then we define these two variables, d1 and d2, right? The distance from the focus to a point on the hyperbola, sorry. All right, using those definitions, that's a lot of math, okay? You know all the math you need to follow this, okay? And it has the reasoning here on the right. I put just this smaller image in case you want to remember what the different values are, okay? The point being, let's see if I can get that to disappear. At the bottom is our equation for hyperbola. So again, you can pause the video and really think through this, or look in the textbook, or you can just keep moving along if you'd rather not think about this. All right, here's the equation of a hyperbola centered at the origin. Look how innocent they look to make this whole complicated diagram. These aren't really much more complicated equations than an ellipse, right? In fact, what is the difference between these and an ellipse? This looks very much like an ellipse. The only difference is the minus sign. If this was plus, this would be an ellipse. If this was plus, this would be an ellipse, but it's not, it's minus, okay? So for an ellipse, the a squared term was always bigger. Not the case for hyperbolas, okay? The a squared term always goes with the transverse axis. Whichever term is positive, here it's x, and it opens along the x-axis. Here it's y, and it opens along the y-axis, has the a term. The positive term is always the transverse axis, whether it's x or y. Okay? So we have a and b. A is the distance from the origin to the vertex, right? Here, it's distance from the origin to the vertex. B, we call this a covertex. It's just a little point that we draw that kind of marks out the edges of this green box that we're going to use for graphing. Okay? So here's the covertex. C are the focus points. Once again, C doesn't show up in the equation, just like it didn't for an ellipse, right? The equation for our C is different than an ellipse, but similar. It is c squared equals a squared plus b squared. Remember, for an ellipse, it was a squared minus b squared. Here it's a squared plus b squared. That's what c squared is, okay? So a lot of this is analogous to ellipses. I hope this looks familiar. All right, so we have our vertex and our covertex. Here's our two covertices and our two vertices. And we could draw this little dotted green box and then connect the edges, the corners of that box with these lines. Here's the equations of the lines. You don't really need to know the equations, but you could think the slopes of them are minus b over a and b over a. Think through that if you want. I don't think you really need to know these equations. I don't think. There might be one or two questions. In this case, it's minus a over b, right? Because a is along the y-axis and b is along the x-axis, right? So it's change in y over change in x. So a over b in this case, change in y over change in x would be b over a in this case, okay? And notice they are not perpendicular to each other. They are just, one is positive, one is negative, right? If they're perpendicular, remember they would be negative reciprocals. They're the same value. The slopes are the same, just one is positive, one is negative. Okay, and these lines, these dotted red lines, form the asymptotes that these curves get close to but never touch. Yeah? So here's, in this case, y is positive, so they open up and down along the y-axis. You can pause this if you want to think about it a little bit more. And what if we shift them? What if the center is not at the origin? Everything is just the same, except the equations, if it's centered at hk, just like we've done with circles, ellipses, any equation, right? At x minus h, y minus k, or y minus k squared, x minus h squared, right? And the math for these things gets a little bit more complicated, but the concept is exactly the same. C squared is still a squared plus b squared, okay?